So to collect data from professional play, we use the website chesstempo.com, which has a large database of chess games. And we decided that our population of interest would be ranked chess games who were played by professionals who have an ELO rating of 2,700 or higher. And ELO is just a rating system in chess and also used in other sports. It's just a number that yeah, it shows how good a player is relative to the competition. So 2,700 ELO, which you see right here, is extremely high, and only 42 players currently have it. So the best 42 players in the world currently have this 2,700 ELO or higher. And but this also includes games that were played, for example, 1913, which is the first game that is recorded in this database. So our population has a size of 13,150, and it's ordered by date. So 1913 is the first, and it goes all the way to 2016. And so what we're interested in is the result of the game. So did black win, white win, or was it a draw? And how many moves were played? So how long did it take until the game ended, which is seen right here. So the result being 1-0 means that so white won and black lost 1-0, and the number of moves was 41. So how did we randomly select of these 13,000 games? Well, we saw that there were page numbers and there were rows. So we decided that we would choose 50 rows and have 200, and we looked how many pages there were, which is 263. So to randomly select, we decided to randomly select 100 games. So the way we did this is by using our calculator function randint, having say with 1 comma 263, and then doing another randint. So the first randint telling us which page we should go to, and the second randint would be 1 comma 50, which would tell us to what row we should choose. So let's say we got a randint of, I don't know, 257. We would go to page 257, and we got a randint of one from the 150 that told us 11. We would count 11 down, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 would be this game, which resulted in a draw, as we see here, and in 38 moves. So this is all we would record. We would only record the result and the moves, and that would be it. We did this 100 times, and it was extremely tedious because, as you can imagine and can see, there's no numbering here, so you would always have to manually count the number. So if you got a number like 23, you'd have to count down to the 23rd one, and that was kind of annoying. Not only that was annoying, but also choosing a page number. So now I'm on page 257, but what if it's on page 130? I would have to press previous, or I'd have to like just jump all the way back. There's no other way you can do this on the site, which was extremely frustrating. But yeah, you get the idea. We'd have to basically press all the way to 130, and then again find then what our randint 50 gave us, 150 gave us, and then select that game. So it was a long process, but in the end we managed, and we collected data for 100 games and recorded the result and the moves.
So here we have a pie chart showing the proportions for the strong computer. So you're in the green, you have the white win rate, which is 0.35. In the orange, you have the ties, which is 0.33. And in the purple, you have the black wins, which is 0.32. So as you can see, they're very evenly distributed, with white still having a slight advantage. Here you see the proportions for professional play. As you can see, the white win rate is 0.32. The black win proportion is 0.16, and the ties was 0.52. And we actually expected this since ties are extremely common in professional play. So here we can see the proportions for a weak computer. And as you can see, the proportion for ties was 0.75, which is a lot more than it should be or than we expected. You have 0.02 for black wins, which is a lot less than we expected, and 0.23 for white wins. What was unfortunate is the high amount of ties, especially the end result of the ties being questionable. The fact that black only won twice out of 100 games was also very peculiar, and every single white win, as I previously explained, was almost identical in the amount of moves and the starting moves. And for this reason, we chose to exclude the weak computer simulations from our tests, except for one. So we did a 2-proportion confidence z-interval for the win rate of white for the difference in proportions between the strong computer and the professional play. So to do this, we plugged in the values into the formula and got the confidence interval of 95% for negative 0.1607 and 0.1007. So this means that we are 95% confident that the difference in proportions of white winning between professional games and strong computer simulations is between those two values. Then we did a 2-proportion hypothesis z-test for the win rate of white for the difference in proportions between the strong computer and the professional games. So our null hypothesis was the probability that white wins in a simulated game is equal to the probability of white winning in a professional game. And our alternative hypothesis was that these two proportions were not equal. All the conditions were met for this, and our conclusion was that we failed to reject the null hypothesis due to the high p-value of 0.65311. As you can see, this is extremely high p-value, and this means that we cannot reject the null hypothesis of the proportions of white winning in both professional games and simulated games being equal. So next we did a 2-proportion hypothesis z-test for the win rate of black for the difference in proportions between the strong computer and professional play. So all the conditions were met for this again, and the hypothesis was that the probability that black wins in a simulated game is equal to the probability of black winning in a professional game. Our alternative hypothesis was the probability that black wins in a simulated game is then not equal to the probability of black winning in a professional game. So this is the p-value that we got of 0.00807, which means that we reject the null hypothesis that the probability that black wins in a simulated game is equal to the probability that black wins in a professional game due to this low p-value. This was pretty obvious when we saw the data in the charts, but now we have mathematical and statistical evidence that this is true.
Alright, so here we see a graph labeled white wins in accordance to the starting move. So we have once the strong computer and once the weak computer. So we see the green shows how often white won when it played its first move on the E file and how often it won on the D file. So for the E file it was 0.353 and for the D file it was 0.33. Now the win rates might seem a bit low, but this is because ties are not excluded. So like we saw before with a strong computer, approximately one third of each win, or one third of the wins were ties, one third were black wins, and one third were white wins. So 0.353 would be when it started on the E file, and 0.33 would be when it started on the D file. Now for the weak computer, we see something bizarre again, and this is again due to the fact that there were so many ties, so the win rate is very low, 0.26, and black didn't win a single game, white didn't win a single game on the D file. So we performed a 2-proportion hypothesis z-test for the win rate of white in accordance to its first move, so E file or D file, for the strong computer only because we decided that it was not reasonable to do with a weak computer because of the weird results. So all of our conditions are met, and we simply plug in all the values, and we get a very high p-value.
So we failed to reject the null hypothesis that the probability that white wins in a simulated game with the starting move being on the e-file, pawn on e2 moves to e4, compared to the starting move being on the d-file, pawn on d2 moves to d4 is equal, due to our extremely high p-value of 0.88329. Again, this was very visible in the charts as the two bars were very close to each other. But according to our test, the starting on the e file or d file does not have an impact on how the game develops concerning white's chances of winning on the strong computer. This bar graph shows the black wins in accordance to response to first move, so it's similar like the last graph where that was showing white's win rates according to its first move, and now this is the same except for black's response move. So as you see, the active and defensive for the strong computer are extremely similar. So you have 0.333 and 0.325, very similar. And then when the computer responded to white's first move with other, so moving, for example, a knight or any other pawn that was not on the e file or d file, then it had a 0.222 win rate. Again, this is excluding, it is including ties, so the win rates may seem low, but they are just adjusted, or they just seem low, but they're actually also including ties. So yeah, for the weak computer, there were only 2 black victories, and both of these were on the active. So the win rate is 0.07, and obviously if there was 2 wins on the active and only 2 games that black won, there were no wins for defensive or other. So again, we see the weak computer being very obscure with its results. Okay, so here's our chi-squared goodness of fit test for black's win rate according to black's first responsive move on the strong computer. So this is referring to the graph that we just saw. And here are the observed counts so the first proportion P1 is for the active. So out of 51 games that the computer that black played the active response, it won 17 out of these. So the proportion was 0.33, but our observed count is 17. And out of the 40 games that black played defensive, it won 13 out of them, so it's 0.325. And out of the 9 games that it played anything besides active or defensive, so other, it won 2 out of 9 games. So the observed counts are 17, 13, and 2. And our estimated counts are just the proportions that we calculated times, the black's win rate proportion, so 0.32 on the strong computer, because that's the win rate that it won overall. And we multiplied that by the amount of games that it played on the active, so 0.32 times 51, so it's expected to have won 16.32 games, and it won 17, so that's pretty close. And 12.8 was expected for the defensive style, and 2.88 was expected from other. Our conclusion is that we failed to reject the null hypothesis that the proportion of wins for black is the same for all 3 different responsive moves due to our high p-value. I didn't tell you guys, but we actually had a condition that was not met, as you may have or may not have noticed, and that is that all expected counts are greater than 1, which is true, 16.32, 12.8, and 2.88, but more than 20% of the expected counts are less than 5. So this is 2.88 is obviously greater than 1, but since we only have 3, 33% are under 5, so that's higher than 20%. Therefore, this condition is not met, but we anyways performed the test and proceeded with caution, like we always do. So we should still not really take these results seriously, I guess, but it's still interesting to see, especially because of our high p-value nevertheless. So the reason, another thing is that on the graph that portrayed this data that we just previously saw, it seemed clear that the category other was an inferior starting move, but our test contradicts this. This is because we only had 9 games where black responded with other, meaning that each game that it won made a huge difference. If our sample size were larger, we could obtain definitive results. So as you see, with other, it won 2 out of 9 times, but had it won 3 out of 9 times, so only 1 time more, then it would have actually been at that 2.88, or would have actually exceeded it.